So on the next set of questions, starting with question 7, we're going to be doing the one mean z-test procedure. So I have put the procedure table here. All right, so let's read question 7. A random sample of 100 healthy adult humans found an average temperature of 98.4 degrees. There were no outliers. Assuming a population standard deviation of 0.75, perform a one mean z-test to answer the question, is there enough evidence to conclude that the population mean of human temperatures is less than 98.6 degrees? Check the test assumptions, and if the assumptions are satisfied, then find the alternative hypothesis, null hypothesis, p-value, and write an interpretation statement explaining your conclusion from the test. So I went ahead and put the sort of question outline here just to help me get through these more quickly. All right, so let's start by checking the assumptions. So the first assumption, A, is that we have a random sample. So do we have a random sample in this question? Well, it says we do. So I'll put yes. B is, do we know the population standard deviation? So we are told to assume that it's 0.75. So that's yes. And then the last one is about sample size, distribution, and outliers. It's a bit complicated, so it's all this. So we have a sample size of 100. So we're in the last situation here. And so any distribution is okay as long as there are no extreme outliers. So we were told that there were no outliers at all. So we're good to go for this last assumption as well. All right, so we can proceed with the test. So now we're going to go through finding alternative hypothesis, null hypothesis, p-value, and the interpretation statement. So we're just going through these steps right here, okay? So first, the alternative hypothesis. So for this, you can refer back to the table here. So this is the claim that you want to show is true. And there's 3 things that it could be: mu is less than something, mu is greater than something, or mu is not equal to something, where mu is the population mean for the population in question. So the thing that you're trying to show is always what is given in the question, okay, the question statement. So is there enough evidence to conclude whatever comes after that is your alternative hypothesis. So our alternative hypothesis is the population mean of human temperatures is less than 98.6 degrees. Okay, so that is the alternative hypothesis. And if you want to write it in symbols, then the population mean is mu, or rather the population mean of human temperatures, that is mu, and then we're saying that's less than 98.6. Okay, so in symbols it would be like this, mu less than 98.6. All right. And so that puts us into the situation of a left tail test where our mu0 comparison value is 98.6. Okay. So we're doing a left tail test with mu0 being 98.6. Okay. Now the null hypothesis is always the direct opposite of your alternative hypothesis. So it doesn't say here whether to put it in words or to put it in symbols, but we can do either one. So the words would be the population mean of human temperatures is greater than or equal. So population mean of human temperatures is greater than or equal to 98.6. Okay, so that's if we're doing it in words, and if you want to do it in symbols, it would be mu greater than or equal 98.6. Okay. And that is also written in the left tail test column up here as well. All right, so next is calculate the z-score. All right, so I'm going to copy this and then I'll put things in their places. Okay, so m is our sample mean, and that was 98.4. Okay, so 98.4. Mu0, that is the comparison value from the hypotheses, so that's 98.6. Sigma is our standard deviation for the population, so that is 0.75. And then n is our sample size, so that is 100. Okay, so this part here is pretty complicated to put into a calculator. If you are doing this in one line on a scientific or graphing calculator, make sure you surround the top and the bottom of this fraction with parentheses like this. okay, because you want to make sure that the order of operations is done correctly. The top and the bottom need to be evaluated first. Now, if you're doing this on a 4-function calculator, I would go one by one. First, simplify the top and the square root. Okay, so on the top, it's going to be negative 0.2. And then on the bottom, I would keep that 0.75 right where it is and evaluate the square root, so 10. Right, and then for the next step, I would do this division that's in the bottom, so 0.75 over 10, which is going to give you 0.075. And then lastly, I would do the fraction, so that's going to come out to negative 2.67. All right, so I have to be pretty careful. All right, so our p-value then, so going back to the table here, we are in the left tail test situation. So for the p-value, you just want the area to the left of that z-score. So you're just looking up the CDF table value, just the regular table value, don't do anything else to it. All right, so this is going to be CDF of negative 2.67, and so I'm going to refer to my table. Negative 2.6 is this row, and then the 7 is going to be this column, so I'm looking at 0.0038 for my p-value. All right, and now lastly for the interpretation, so I'm skipping over this optional thing here. For the interpretation, you have to decide if p is very small or not very small. I think I added this word very since the last time I showed you the table. You guys were going with p-values that were too big. So p needs to be small enough that it's a probability that you would be very, very surprised if an event with that probability actually happened. Okay, so as a probability, this is 0.38%. So if an event that has a 0.38% probability happens, are you going to be surprised? Well, yeah, I think that's pretty surprising. It's less than 0.5%, so like a 1 in 200 chance of happening. Yeah, I'd say that's pretty darn surprising. So I'm going to say that p is very small. So my interpretation will be with a p-value of whatever it was, there is, I guess I'll go with strong evidence to conclude that, and then I'll put the alternative hypothesis, okay? So with a p-value of 0.0038, there is strong evidence to conclude that, and then you can literally just paste in whatever the words were from your alternative hypothesis or from the question that was originally asked in the problem. Okay. Right, so for number 8, we're going to do the same thing. So we're going to start by reading the question. A random sample of 25 ducks found that they quack 6 times per hour on average. There were no outliers. Assuming a population standard deviation of 4 quacks per hour, perform a 1 mean z-test to answer the question, is there enough evidence to conclude that the mean quack rate of all ducks is different than 5 quacks per hour? Okay, so we're going to do the same stuff here. First, we'll check the assumptions. Was it a random sample? It does say random sample, so yes. Do we know the population standard deviation? Let's see. It is told here that that we should assume it's 4. So we'll go with yes. And do we have the right sample size distribution or lack of outliers? So here we have 25 ducks. So referring to the whole table here, we are in the second situation. Sample size is 15 to 29. Any distribution is okay as long as there are no outliers and the distribution is not extremely non-normal. I don't know about this, whether it's extremely non-normal or not, but there's no outliers. So if there's no outliers, I think that should be good to go. All right, so now for the alternative hypothesis, I'm just going to take that from this question right here. Is there enough evidence to conclude that, and then whatever comes after is the alternative hypothesis. Okay, so there it is. The mean quack rate of all ducks is different than 5 quacks per hour. So now in terms of the symbols and which of these situations we're in, is it a left, a right, or a two-tailed? So different, it means not equal. So we are in the two-tailed test situation. Mu does not equal, and then the value that I want to say that it's not equal to is right here, 5 quacks per hour. Okay, so in symbols, this would be mu not equal to 5. So mu is the mean quack rate of all ducks, and then 5 is my mu sub 0 value for the to put into the z-score formula. All right, so we're doing two-tail test, and mu 0 is 5. All right, so the null hypothesis is just going to be the exact opposite. In fact, maybe I will just copy and paste this and change a couple little things. So the exact opposite would be equal to 5 quacks per hour, and then this will be equal as well. All right, so now for my z-score, I'm going to plug in all the numbers that I know. So m is the sample mean, so that is given in the first sentence here 6 times per hour on average. Mu 0 is the comparison value from the hypotheses, so that is going to be 5. Sigma is the population standard deviation, so we're given 4 for that. And then n is the sample size, so that was 25 ducks. Okay. So simplifying carefully here, I'm going to do the top and the square root. So 6 minus 5 is 1. Square root of 25 is 5. Now I'm going to simplify the bottom. So 4 over 5 is 0.8. And then finally I'm going to do 1 divided by 0.8. And I get 1.25. Okay, so that is my z-score, 1.25. And now I need the p-value. So in this case, I'm doing the two-tail test. So it's important I look in the right column here. So for two-tail test, I want to do p-value of 2 times the CDF of negative absolute value of z. So what that means is twice the area to the left of the negative version of z. So by taking the absolute value, first I make the z value positive, and then I stick this negative on it. So basically it's like forcing the z value in here to become negative. All right, so regardless of whether you got a positive or minus a negative z, you use the negative version of it, you look up the CDF in the table, and then you double it. And the reason is because you're doing two tails, so it's this like symmetrical situation where the tail to the left of the negative version and the tail to the right of the positive version have the same area. All right, so anyway, coming back down here, I'm going to do 2 times the CDF of negative 1.25. All right, so let me go to my table and look up negative 1.25. So negative 1.2 is here, and then 5 is going to be this column. Okay, let me come back down. So it's this column. All right, and then negative 1.2 is here. Okay, so I'm looking at 0.1056. 0.1056. All right, and then I'm doubling that, so that's going to become 0.2112. All right, so you have to ask yourself, if an event with that probability happened, would I be so surprised that I would reject things I previously thought might be true? Not really. That's like a 1 in 5 probability is not that surprising. Generally, you don't want to say that p is small until it's at least below 5%, and some people think they should go even smaller than that. So 5% is like the maximum place I would call p small at. So definitely not 21%. So this is a situation for the second interpretation when p is not very small. With a p-value of whatever it was, we do not have enough evidence to conclude, and then whatever you wanted to conclude. All right, so the interpretation is with a p-value of 0.2112, we do not have enough evidence to conclude that. And then what we wanted to conclude was mean quack rate of ducks is different than 5 quacks per hour. So even though we got 6 quacks per hour, the standard deviation was big enough that at 4 quacks per hour, that is what is causing us to not be able to conclude that it's different than 5, even though we got 6, which is, somewhat different than 5, is not different enough given that standard deviation. Okay, so let's look at the last one of these. A random sample of 40 cats found an average tail length of 12 inches. Assume that tail lengths are normally distributed with a population standard deviation of 2 inches. Perform a 1 mean z-test to answer the question, is there enough evidence to conclude that the mean tail length of all cats is greater than 11 inches? Check the test assumptions, and if they're satisfied, then we do all these things. So I've put the little outline here. And so for our assumptions, do we have a random sample? It says we do, right there. Do we know the population standard deviation? It says that it is 2, so yes. Sample size, okay, with the distribution and outliers. So our sample size is 40. So looking back at the guidelines, for sample sizes 30 and up, any distribution is okay as long as no extreme outliers. Okay, so in this situation, I don't know how you would have an extreme outlier in cat tail length. It's not like any cat has a 2-foot long tail or anything. I guess some cats have really short tails, but that would constitute some sort of injury or like a special breed. All right, so it does say, where does it say it? Oh, it says assume that they're normally distributed. So in that case, it's actually okay no matter what the sample size is, even if it's very small. So yes, we're good to go here. All right, so alternative hypothesis, again, I'm just going to take this from the question. Is there enough evidence to conclude that, okay, so here's the alternative hypothesis right here. The mean tail length of all cats is greater than 11 inches. So I'm just going to paste that in here. Oops, sorry about that. Keyboard shortcut gone awry there. Okay, so, and then if I want to put that in terms of symbols, so the mean tail length of all cats, that is my mu. And then I have greater than 11, so greater than 11. Okay, so in this situation, what kind of tail test are we doing? Looks like we're doing the greater than version, so this is a right-tailed test, and my mu0 is going to be that 11 number. Okay, so this is right tail, and mu0 is 11. Okay, so null hypothesis, I'm just going to actually paste this and then change it to be opposite. Okay, so mean tail length of all cats is going to be, so instead of greater, I'm going to say less than or equal to 11 inches, and then here I'm going to also change to be less than or equal. All right, now for my z-score. Just going to plug everything in. So m is the sample mean, and that was said to be 12 inches. Mu0 is the value from my hypotheses, that is 11. Sigma, standard deviation, they've told me here that it is 2. N is the sample size, and we have 40 cats. Okay. So I'll just go ahead and do this one pretty quickly. So I got 3.16. And now for the p-value, let's make sure we do it the right way. So for right tail test, to get p, you do 1 minus the CDF. So you look up the area in the table, and then you do 1 minus that. So that's for right tail. Okay, so we're going to do 1 minus CDF of 3.16. All right, and let me look at my table. So 3.16 is going to be 3.1. Okay, so here's 3.1, and then 6 is going to be, all right, so it goes 0, 1, 2. All right, so this will be 0, 1, 2, 3, 4, 5, 6. So it's going to be this one, 0.9992. So 0.9992. Oh, and I am subtracting that from 1, which is good because otherwise it would be really big. So I get 0.0008. And as a probability, that is quite small. It's less than 0.1%. So you'd have a 1 in 1,000 chance, approximately, of that event happening. All right. So kind of the summary of what's happening here is if the null hypothesis is true, then there's only a less than 1 in 1,000 chance that we would have gotten the sample data that we got. Okay, so then we say, okay, I don't think the null hypothesis is true, so probably the alternative hypothesis is true. All right, so our interpretation statement here is going to be with a p-value of 0.0008. There is, I'd say this is very strong evidence to conclude that, and then whatever we wanted to conclude. Okay, alternative hypothesis. All right. So that is the end of that type of question. The next set of questions is about t-tests. So you are not going to have Excel on this part of the test, but you can still answer a lot of the questions from the t-test procedure without using Excel. So for example, like I'll just tell you what the p-value is, and then I'll show you the box plot and the sample means and stuff. All right, so let me get the procedure table and put it down here. Okay, so I've pasted that in, and now let's read the question. Amongst all American movies from 2022, a sample of 23 animated movies and a sample of 25 live-action movies were randomly selected. The worldwide box office for each movie is shown in the picture below, along with a box plot and the mean for each sample. Perform a one-mean t-test to answer the question, is there enough evidence to conclude that in 2022, live-action American movies had a lower mean worldwide box office than animated movies? Okay, so this is real data that I really got from the internet, and I really got like the right p-value down here and stuff, so it's not a made-up question like the cattails and the ducks and stuff. All right, so first, does the sample data pass the assumptions for the one mean t-test? And then if it does not, you skip the rest of the parts. Okay, so the two assumptions you have to check are random, and then this same exact thing as for the z-test about the sample sizes and the distribution. Okay, so for the answer here, oops, okay, oops, what's going on? Okay, so yes, we have a random sample, and the sample size is 23 and 25. Okay, so for both of those, they're in the second category, sample size 15 to 29. So any distribution is okay as long as there are no outliers and the distribution is not extremely non-normal. So let's look at our distribution here. Okay, well, I'm already seeing, not only are these outliers, I would call these extreme outliers. So instead of the word and here, I'm gonna put the word but, and take away this yes here. So this is a no. We have a random sample, but the sample size is 23 and 25, and we have actually many outliers. Some are even extreme. So this does not pass the assumptions. Okay, so we should not proceed with the test here. We're just going to do what it says here, where it says skip the rest of the parts below. All right, well, that one was pretty easy. So let's try number 11. A random sample of 17 100 level sections and 16 400 level sections were selected from all the sections offered at SU in spring 2023. Again, the real question, I really did this. The number of students in each section is shown in the picture below, along with box plot and the mean for each sample. Perform a one mean t-test to answer the question. Oh, this should say two mean t-tests. Sorry, that's just a typo. Is there enough evidence to conclude that in spring 2023 at SU, 100 level sections had a higher number of students on average than 400 level sections? Okay, so first we check the assumptions. So it does say that we have a random sample, and I really did sample randomly, I promise you. And the next thing is about the sample size. So we got 16 and 17, which is in the second category here, so 15 to 29. So we just need to make sure there's no outliers. Right, so looking at the box plot, I don't see any outliers, so we should be good to go for that. Okay, so we do have a random sample, and with sample sizes 15 to 29, we just need no outliers, and there are no outliers. Okay, so we're good to go here. Good to go. Good to go. Good to go. All right. So part B, what is the alternative hypothesis for the test? Write the hypothesis in symbols using mu1 and mu2, and also in words using words like section, students, etc. Okay, so I'm just looking at the question again up here. Is there enough evidence to conclude that? And then whatever comes after that is the question. So in spring 2023 at SU, 100 level sections had a higher number of students on average than 400 level sections. That is the alternative hypothesis. Okay, and now I will turn that into some symbols. So for my symbols, mu1 and mu2, because we have two different means. So the 100 level sections, number of students on average, and then the 400 level sections, number of students on average. That's my mu1 and my mu2. Now don't forget that in the table here, I only have it set up for you to say that one is lower than the other. So whichever one you think is higher, that's going to be your mu2, and then whichever one you think is lower, that's going to be your mu1. Okay, so let's see, come back here. So I'm going to always write it like this, mu1 less than mu2, is okay if you turn it around. I just didn't put a column in the table for that, but if you can figure it out yourself, that's fine. I'm just going to stick with what I have in my table, which is like this. So that means that mu1, the one I think is lower, is actually the 400 level sections, according to the way this question is written. Okay, so it's going to be 400 level mean, and then mu2 is going to be the 100 level mean that I think is higher. Okay, so that is our alternative hypothesis in both forms, and then I've told you which one is mu1 and mu2. So next question is, do the sample means match the alternative hypothesis? And if they don't, then you have to skip the rest. You can't do the test. Okay, so what I mean by match is, like, is it true that the sample mean for population 1 is actually less than the population mean, or sorry, the sample mean for population 2? Or if you want to look at the word version, is it true that the sample mean for 100 level sections is higher than the sample mean for the 400 level sections? Okay, so just looking at our box plot here, you can see the means are where the x's are, or you can look at, I actually calculated the numbers up here at the top. So the 100 level sample mean, yes, it is higher than the 400 level sample mean. All right, so yes, the 100 level sample mean is higher than the 400 level sample mean, or another way to say it, if you want to put it in symbols, is M1 less than M2, where M1 is the mean for the 400 level classes and M2 is the mean for the 100 level classes. Okay, so those means again were just 13.8 and then 20 point, just rounding them a little bit, 7.1. All right, so null hypothesis for the test. Write the hypothesis in symbols and in words. So I'm just going to copy my alternative one, and then I'm going to reverse the words, all right, or make them opposite. So instead of the word higher, I'm going to say less than or equal. And then instead of the less than symbol here, I'm going to do greater or equal. Right, so the null hypothesis would be that the 100 level sections have a less than or equal number of students on average than 400 level sections, or to put it into symbols, mu1 greater than or equal to mu2, where mu1 is actually the 400 level classes means. Okay, now the p-value, I actually went ahead and did it for you in Excel, and it was 0.0125. So what interpretation statement should we select? So looking at our interpretations here, they're actually exactly the same as for the one mean z test that we just did. And they're exactly the same for the chi-squared test that we're going to do next as well. In fact, really any hypothesis test, if you have a p-value, you can use these interpretation statements safely. So just think about if the p-value is small or not. And by small, I mean like at least less than 5%. So my interpretation statement here would be, this is about 1.25%, so yeah, it's pretty small. It's not super small, but it's pretty small. So I would say with a p-value of 0.0125, there is enough. I'm not gonna say it's strong, but it's enough evidence to conclude that. And then I'm just gonna literally paste whatever the alternative hypothesis was. Okay, and there it is. All right, so that is it for that one. And now let's look at number 12. All right, so another real question. Amongst houses listed for sale in Selinsgrove, a random sample of 32 from 2019 was compared to a random sample of 35 from 2022. The list price of each house is shown in the picture below, along with a box plot and sample means. Perform a, this is another typo, two-mean t-test to answer the question, is there enough evidence to conclude that the mean list price of Selinsgrove houses was different in 2019 than 2022? Okay, so first we need to check the assumptions. So the two that we need to check are, was it a random sample? And then we have to look at the sample size and outliers and stuff. So it does say random sample. For the sample size, we have 32 and 35, and we have no outliers in the picture. So just double check with the chart here, but yeah, we are good to go. No outliers at all. All right. So the answer here is going to be yes. We have a random sample and 30 plus sample size with no outliers. So that is good. alternative hypothesis for the test. So again, I'm just going to jump to what is it that I want to conclude in the question. Mean list price of Selinsgrove houses is different in 2019 than 2022. So that's going to be my word version, just directly pasting it right from the question. And then in symbols, this means that the two means are just different, just not the same. So mu1 not equal to mu2. And I can assign whichever one I want to be mu1 and mu2 because I don't have to worry about which one is bigger or smaller. Okay, so I think I'm not even going to worry about which one is which. I'll just, if I need to assign them at some point, then I'll think about it then. All right. Now, do the sample means match the alternative hypothesis? So we're actually doing the two-tail version here. If we look back at the table, we're in the two-tailed test column here because we want to have mu1 not equal mu2. So all you need to check is that the means are not the same, and it would be really shocking. I mean, it would be quite a coincidence if they were, so you don't really have to worry about this one as much for the two-tailed version. Oh, I'm sorry, I'm on the wrong part. Okay, so yes, the two sample means are not the same. You can see that from the position of the x's on the box plot, or you can look at these two numbers up above here that I calculated for you. Okay, null hypothesis. I'm just going to take my alternative. I'm going to copy it, and then I'm going to make the words opposite. Okay, so mean list price of Selinsgrove houses was the same in 2019 and 2022, or in other words, mu1 equals mu2. Okay, so that is the null hypothesis. And now my p-value is the probability that I would have gotten sample data like what I got if that null hypothesis were true. So assuming the p-value is 0.194, write an interpretation statement. So 0.194 as a probability is 19.4%. If an event with that probability happens to you, I don't think you should be that surprised. I mean, maybe a little bit, but not much. So this is not low enough to make a conclusion. So our interpretation here is going to be with a p-value of 0.194, there is not enough evidence to conclude that house prices, well, let me just copy whatever it even was. The mean list price of Selinsgrove houses was different in 2019 than 2022. Yeah, so basically the housing prices did not really change that much. It was only a 3-year period, so not too surprising.